So now we're going to learn about another process of division that's more efficient than long division, but can only be used in certain situations. So I've given you a long division problem here, and you can see I've sort of already worked it out. And we're going to use this as a foundation for learning about this new process, which is called synthetic division. Now, mathematicians, when they have to repeat a process over and over again, often look for a more elegant way of doing the process. And elegance for mathematicians means easier, shorter, faster. So mathematicians often had to use polynomial division to determine whether binomials were factors of polynomials. So they were looking for a more efficient way of doing this polynomial division. So I'm going to flash over here, take this problem to the next. So we've learned about the process of long division, which is a useful way of dividing polynomials by each other. We are also going to learn another method of division called synthetic division that's more efficient than long division is, but only works in certain circumstances. So what I've got here is a long division problem that I'm going to use to sort of model what synthetic division looks like and to explain why it works. So in order for synthetic division to be used at all, the restriction is that the divisor, which is the thing you're dividing by, has to be a linear binomial of the form x minus a. So basically, a linear means as power of 1 is the biggest power on a variable. Binomial, 2 terms. Form x minus a means there can't be a coefficient on the x. And we'll explain why that's important for this process in just a moment. So this is a long division problem that I've finished, and I'm going to take that problem to the next screen. We're going to talk a little bit about the numbers themselves in this problem, not just like the whole division, but the numbers that appear in it. So if I look at this dividend and I look at the coefficients that are in there, I'm going to write those down in a row like that. Now the synthetic division process is basically going to be doing sort of what long division does, except it has as those assumptions that the coefficient on the x is 1 and that the degree of the thing you're dividing by is 1. It's a linear binomial. So when I look at the numbers that appear in the answer from my long division, you see this 2 right here came from the fact that this was a 2 there, and this, when you divide it in, doesn't change what you get there. So since that's a 1, this number here would always be the same as this. So when I'm doing synthetic division, I could actually bring down that first number because it's always going to be the same because the coefficient on the x term is 1. Now if I look at the other numbers that appear, now keep in mind every time I do the long division step where I'm subtracting, the first terms right here always subtract away. So we're going to ignore those for just a minute. And instead, we're going to focus on these numbers that appear. Now, that 11x that was sitting there came from 2 things. It came from the original coefficient that was sitting there, and it came from this -6. And the -6 came from that number times that number, right? And then those things got subtracted and it gave me 11x. Well, if I look at the next number, the 29, it came from 2 things. It came from this 4, right? -4 right here, and this -33, which was 11 times that -3. And then these 2 things got subtracted. And if I look at the 29, that's what I just looked at. If I looked at the 94, it came from this 7, which was brought down from here. And then it came from this -87, which was this 29 times -3. So you see those numbers that we're getting in this synthetic division process basically are happening the same way every time. They're coming from one of the original coefficients, and then you're subtracting away a product of the previous number you got in a step and the constant term of that linear binomial that is the divisor. Synthetic division is built entirely upon this. So if I were to take this linear divisor, and instead of treating it as x minus 3, I just treated it as the thing that makes it unique. Keep in mind, this is a linear binomial, and it has to have a coefficient of 1 on the x. So all those things you're divided by are going to look like x minus something. So the thing that makes them distinct is what that something is. So if I were to actually take that negative 3, and I were to write it right here, keep in mind, this negative 6 that I got, that's going to be subtracted from the 5, came from 2 times negative 3. So that was basically the first coefficient we had times that binomial, times the constant from the binomial. So if I took this number, which is the constant from the binomial, and I multiplied it by this number, which is that first coefficient, that would give me negative 6. And that would line up in the next column with the next coefficient, as you can see right here. And then if I take those two things and take what I did in long division and basically subtract those, 5 minus negative 6 is positive 11. And you see that gave me the 11 that's here. Now if I wanted to get this 29, that 29 came from this negative 4, which is right here, and this negative 33, which is that 11 times the negative 3. So if I were to take this negative 3 then and multiply it by the 11, that would line up with the negative 4. And then if I subtract those, I would get positive 29. Well, you're starting to see a pattern, I hope, in that in order to get the next thing, this negative 87 that I got here, it'd be negative 3 times 29, it's negative 87, and then I subtract those. Now, what I got here at the end, notice I've run out of numbers, and what I got here at the end was the remainder I got from my original problem. So I'm going to box that off. Now, because we started dividing by a linear binomial, which is that power of 1, my original powers on all the terms should decrease by 1. So if I started with a 2x cubed, this thing then should now be a 2x squared. And this thing should be a coefficient on the next term down, which would be an x. And this would be the coefficient on the next term down, which would be x to the 0, which is just a constant. And then this thing we said was the remainder. And remember what we do with the remainder is we divide it by the original divisor. So this is where synthetic division came from. It was basically trying to find a shorthand way of doing long division. And look at the advantages that you get. Long division can take up, I believe this one took up like 7 or 8 lines on a piece of paper. The synthetic division problem basically took up 3 lines. Now I will say, in order to keep the calculations easy, the synthetic division algorithm has changed slightly over the centuries. So this, what I'm about to show you right now, is what the algorithm looks like now. And this is the way that we're actually going to do it. So the difficulty was in getting the subtraction correct every time, because subtracting is slightly more difficult than adding. So what happened is when they set up synthetic division stuff, you'd write the coefficients of the dividend here, but in the box, instead of putting the number that appears directly there, what we do is we put the number that you get when you let the divisor equal 0. So what that is going to give you 3. So what's going to happen now, you notice how that came out as the opposite sign of what we started with? That's intentional, because now every time when we're doing the algorithm, instead of having to do that subtract step, we're basically going to be adding the negative of what we would have been adding before. So what we would have been subtracting before. So if I bring the 2 down now, and I'm going to start doing by this multiply, and then instead of subtracting, which is what I would have done before, I'm going to instead add. because that's the negative of the number that we would normally have in there. And that would give me 11. And then I multiply. And add. Multiply. And add. You can see it's marginally easier. I mean, the difference isn't great, but anytime you're trying to do a bunch of like a particular type of calculation, anytime you can save is good. So we're going to box that remainder off. And the answer will be the same as what we got before. Now, I'm just going to walk through a couple of quick synthetic division problems so you can see them in. So here is a new one. So I'm going to do this by synthetic division, and I'm going to get rid of my stray mark there because that's useless. So I would start by taking the dividend and writing its coefficients out. Now keep in mind, if you were missing any terms in the dividend here, you would absolutely have to put the 0 in as a placeholder. Remember, we talked about that with long division. It's super important in synthetic. So I'm going to put a box off to the side. And in that box, I'm going to put what makes x plus 4 equals 0. Well, that would be negative 4. I'm going to bring the 1 down. And then multiply. That goes in the next column above the line. And then add. And that would give me 1. Multiply, add. Multiply, add. Last number is the remainder. So this is the coefficient of a term that is 1 less than what we started with. So this would be 1x squared. This would be 1x. This would be 0 as a constant. And this would be the negative 3 remainder. Now, here's another problem, and I'm going to change it slightly so we can see how this works. Let's get rid of that negative 7x term. All right, so if I divide this using synthetic division, first of all, writing the dividend would be 4, 6, 0, and 3 normally. But there's a rule, remember, that says synthetic division only works if the thing you're dividing by has a coefficient of 1, not 2. So what we're going to do is this. We're first going to adjust this division problem so that it's legal to do by synthetic division. And the way we're going to do that is we're going to split out that coefficient that's on the x. And then that, if we divide it into each of the terms on top, oops, and then go through the synthetic division process with the x minus 1/2, then we're going to get a good result. So now I'm going to write the coefficients of the dividend, 2, 3, 0, remember, because we don't have an x term, and it's really important to put that placeholder if you're missing it. And then 3/2, little box. In that box goes what makes x minus 1/2 equals 0, which in this case would be x equals 1/2. Bring down the 2 and begin. So 1/2 times 2 is 1. Add. 3 plus 1 is 4. 1/2 times 4 is 2. Add. 0 times 2, sorry, 0 times 2, 0 plus 2 is 2. 1/2 times 2 is 1. 3/2 plus 1 is 5/2. And then 2x squared plus 4x plus 2 with a remainder of 5/2. Now you could write 5/2 over x minus 1/2, but that's really a pain. Stacked fractions are not fully simplified. So what I'm going to do instead is simplify that fraction at the end. And keep in mind that since you're dividing 5/2 by x minus 1/2, it would basically look like 5 over 2 times x minus 1/2, which is 2x minus 1. I hope this helps.